All right. All right. It's really great to see everyone here for the CHDH hosted panel debate. Debate is not a good word. Started off terribly already. Discussion about what large language models tell us about human cognition. Before beginning, I would like to acknowledge the traditional owners of the land, the Wurundjeri people, who have not ceded this territory, and pay my respects to their elders, past, present, and emerging. I would also like to introduce myself and the discussants, although they'll tell you a little bit more about themselves as they go and tell you a little bit about the structure of this. So I'm Professor Andy Perforce. I'm the director of the Complex Human Data Hub, and kind of cooked this up because it was very evident through many discussions with many people that A, large language models are really interesting, B, that they're interesting to cognitive scientists for an additional reason to that they're interesting for everyone, although I guess everyone's interested in this topic on some level, which is what they tell us or don't tell us about human cognition. So that's what the focus of this panel is. There's a lot of other interesting questions we won't have time to get into, but I think this is more than enough for an hour. So the three people talking today are all experts, both on different large language models, and also different aspects of human cognition. So Professor Simon Dennis has been working on large language models and their precursors for a very long time, and is also an expert in human memory and representation. Kat Vylomova is a lecturer in the School of Computing and Information Systems and a computational linguist. So she does a lot with large language models, and she's thought a lot about human language and how we think and use it. And Simone Deyne is really a world expert in semantic representation and human concept learning, and does a lot with sort of comparing, again, human representations and how we think about these things to how large language models do. So we have some excellent panel members. The structure of this is, because this is a pretty heterogeneous audience, we're going to basically ask Professor Dennis to give 10 minutes quick intro to large language models, which will be both probably too much and not enough simultaneously, but hopefully get us mostly on a similar page, because I'm sure some of the aspects of the discussion will turn on actual details of how they work. And then I've got two basic questions, which I'm going to pose to the panel. One about what they tell us about the human mind, and one about how we can use them in cognitive science. And hopefully we'll have time at the end for questions from the audience. Okay, so try to hold your questions, especially if they're big thought questions, till the end. If you have something that's sort of, a very fast understanding question, go ahead and ask at the time, but that's how we'll try to do this. And I'm going to be pretty ruthless as to time. So I swear I'm a nice person normally, but it won't be evident now. Simon, go on.
Okay, thanks, Andy. Yeah. So welcome, everyone. So as Andy said, my main areas of interest are in human memory, but I've been doing neural net connectionist modeling, as it used to be called, for a bit over 30 years now. And in fact, my thesis work looks surprisingly similar to the transformer model. So I can tell you about that at another time if you're interested. But my job today is to give a very basic understanding of how the transformer model works. I'm going to be throwing out a whole bunch of technical details which are actually important if you actually want to make them work. But I really just want to focus on giving you a kind of high-level understanding of what's going on. So the basic task that the transformer sets up is to predict the next word. Okay, so we've got a set of words. We want to predict the next word, given the context. And so the question is, how do you go about doing that? So for instance, let's say you've got, I always found Janice amiable, but not everyone likes, and now you have to predict what comes next. So a good completion might be a word like her. So that's basically all it's doing. And in order to create larger sequences, it's basically taking its prediction, putting it into its context, adding it to the context, and then making another prediction, and continuing to do that until it predicts that it's got an end of response. So the real question, the way that transformer models that underpin the latest LLMs differ from previous models is the way that they understand how to extract the information from the context in order to make a prediction. So if you think about it, this is one of the limitations of earlier models, they were tended to be focused very much on the last few items, okay? So if you think about this sentence, if you only have the last few items, not everyone likes, then there are lots of possible completions, right? So it could be him, football, her, politicians, etc. Right? So in order to actually isolate what's really appropriate in this context, you need to go back further. And in particular, there are certain words from the context that are important for making the prediction and other words that are not so important. Okay, so in this case, we've got, I always found Janice amiable, but not everyone likes her. So you really need to get information from the Janice token in order to realise what an appropriate completion would be here. And the other critical thing is that you want to be ignoring some of the intervening words, even though they've occurred more recently. So things like amiable and everyone, you want to be able to ignore those. So how does the model go about it? Well, it starts with the context on this side, the yellow boxes. And those boxes contain vectors which represent the meaning of each of those words, but also the position of those words within the context, which also matters. Okay, so we start there. And then there's a transform, which turns that into a key. And so the key you can think of as like a set of types. So it's me in this position, what kind of thing am I? Okay, so for instance, for Janice, the type that it might generate is something like I'm a person. So that's what it's doing, and it's doing that for everything that's in the context. The next thing it does is it takes the immediately preceding word, so likes, and it generates a query, okay? And the query is, so now it's trying to, remember, it's trying to predict what's coming next. And so the query is designed to say, what types of things do I need to find in my context in order to be able to answer this, to make the next prediction, okay? So in this case, one of the things it might do is say, I'm looking for a person. Right. Then what it does is it goes back and compares the query vector that it generates to all of the vectors, all of the key vectors that were generated from each of the tokens, right? And so the query is saying, I'm looking for a person. The key vector is saying, I am a person. And so it goes back and it says, okay, Janice is probably a word that's going to be important for answering this particular query, or making this particular prediction. Now, in addition to doing that, what it's doing is also generating another vector, which is called the value vector. And that is also a set of types, which gives information that might be important for making the prediction, okay? So knowing Janice is the right word to think about in terms of making the prediction is one step. But then what aspects of Janice? So Janice could have lots of different characteristics, but what ones do I want to project up to be that are going to be important for making the prediction? And so in this particular case, the thing that's important about Janice is that Janice is female, right? Because that's going to be the distinguishing thing that allows us to make a specific prediction later. So you can think of the value as another set of characteristics that that each item is projecting. Then all of those value vectors are added back down into an output vector by virtue of the weights that are associated with each of these tokens. So in this case, Janice would be the primary thing that would get added back in, and the value for Janice would then be in the output, and then that output would then be used to make a prediction. Okay, so that's the general idea about how it works. Sorry, and I just should say, and then of course you do many, many layers of this. Okay, so that's where the complexity really comes in. Now, the other thing, so in that case, right, there was a single word that was really important for discriminating, but it may not be the case that it's a single word that's critical, right? It may be a set of words that sets some kind of stylistic or something like component, something like that. So for instance, let's say we've got, "Oh, sweet melancholy, dost thou pierce my soul with thy bittersweet," right? So after bittersweet, you might think candy, but it doesn't really fit that context, right? And so in this context, you might say lament is a better option. And so what will happen now is, instead of just focusing on an individual item, the attention will get spread across all of those relevant items, okay? Because they will all have a component related to style. And so then you can isolate, you know, should it be lament, should it be candy? But at the same time, we might want that general stylistic thing, but we might also need information about what specific word should be here, right? The style gives me a whole bunch of words that could be relevant, but I also want to know the specific word. And so therefore, it's useful to have more than one of these so-called attention heads, right? So we've got one here that would be doing the job like finding genus. We'd have another one here that's doing a job like finding the stylistic content of the context. And then we bring both of those together in order to make our prediction about what should come next. Okay. And I think that is it from me. So that's the basic idea. Whole bunch of details I left out, but hopefully that gives you the enough to kind of get a sense of what's going on.
Perfect, thanks. Can you stop sharing your screen?
Yes.
Awesome. So what I'm going to do then is share my screen now. So sorry. I'm just going to ask the question while they're answering. We'll figure out the sharing screen. So our first question then, and thank you, Simon, for a nice general introduction. Our first question is basically, so what does this tell us about humans, if anything? And I think you can sort of, all of you can feel free to weigh in on the good, the bad, you know, nothing, everything, and why. And I think we're going to have three sort of different views on this, I think. Yeah.
Start. Maybe I can
go
just
ahead.
walk.
Yeah, absolutely.
So I'm Hess, I'm doing natural language processing stuff. So I'm coming from that particular school of thought. And I'm focusing on computational morphology because it's all about like systematicity and regularity. And this is a kind of aspect at which those transformer-based models are really good at. So, and even though those architectures such as RNNs, recurrent neural networks, they come from this cognitive science. So if you look at 1980s, so most of the debate in 1980s was about like how well they actually model human generalization, so human-like error. So they focus on these architectures with respect to how much they reflect human language. But then in early 2000s, our like field at NLP, it moved from kind of this rule-based approaches to machine learning stuff, incorporating these architectures, and was sponsored mainly by industry. And industry had particular engineering tasks, not much related to the way human learn language. So the task, for instance, like language modeling, so you do not try to understand how humans predict the next word. Then it's probably not the usual task they would do, right? But in these models, you focus on this, the accuracy, basically, how well your model predicts what comes next, what are possible words. So, and you look at these characteristics such as like perplexity, the entropy you have. So, and based on that, you, of course, this is the prediction. So this is what you optimize. And you have this huge models with billions of parameters. As Simon mentioned, there's matrices and vectors. It's all about fitting particular weights and numbers. So you have this initial model that's like, if it's large language model, large means how many parameters you have. You initialize this weight with some small numbers, and then you have a huge corpus Wikipedia, etc., to train this model on to fit this particular weights, to get this particular vector representations of words. So each word gets a particular representation as a long vector of real values, like 1,000 of such. And the way you do this prediction thing. And obviously people don't do that. So babies do not learn language by going through Wikipedia corpus, right? So it's obviously not the task you would do. And they don't require that much data. And now the question is what you can learn from this task. So whether, for instance, like whether you can learn arithmetics by doing this next word prediction task. Who thinks you can learn arithmetics? Someone thinks. Okay, so you can learn single digit multiplication. A single number, like a single digit number by single digit number, the multiplication, but it's mainly about memorization. So if you go with higher orders, like 3-digit number by 3-digit number, you can check it with ChatGPT, it will fail. Because this is qualitatively different task, and it requires qualitatively different approach. So it's not something that you will learn by just predicting what comes next. You can also try another task, such as you get a sequence of, say, ones and zeros, right? So for instance, like 30 of ones and zeros, and ask the model, count the number of ones. It will fail. So most likely it will fail. It's not something they cannot do properly. What they can learn eventually using this next word prediction is to distinguish grammatically correct and plausible sentences from ungrammatical and implausible. And they also can learn style. For instance, you can generate some songs in the style of someone, right? It's really good. So it's very good at capturing regular patterns. So what you can learn from language, from the language side. So you can learn grammar. You can learn parts of speech, right? So if you have cat, dog, etc., so they share lots of the, contextual usages, and this is the idea behind this predicting of the next word. So this meaning of the word can be kind of reduced to the contextual words that appear next to this word. So it's kind of meaning equals to context. So it's kind of Wittgenstein and from kind of structuralism, and it's kind of this vector representations, they are kind of optimized in order to match the contextual words. So these words that collocate, they will have similar meanings. Okay, so it's clear? So, and of course, there are certain limitations with this approach, what you can learn, what you cannot learn. So you always have some training data. So what you want to replicate is this statistical, this distribution that you observe in the training data. If your new data is completely different, your model will just fail on this. So there's a general kind of problem with such models that if you have something out of distribution, right? So you have observed, like, for instance, animals, and then in the test you have something about like sports, right? So they will fail at this. So what they do well is capturing this grammar, parts of speech is kind of generalization. So you have like cat runs, dog runs, etc. So they share contextual usages of animals, some properties of animals, and also they share the property of being noun in this noun kind of role. And they also do well in some meta-linguistic learning. So they can learn the syntax dependency. So you can, for instance, provide even like ChatGPT or any other model with this sentence. I saw a man with a telescope, it's ambiguous, and the model understands that it's ambiguous. It provides a different parsing for each option. Now the question is whether the model understands anything. So when it produces you some sentence, whether you can say that it understands. Probably not, because it even doesn't understand that it doesn't understand something. So it can produce some completely misleading sentence in a very affirmative way. This is why it's dangerous. Like, you never know where it goes wrong. So it never knows what it knows and what it doesn't know. There is no way for this model to form a hypothesis. or for instance, a way to form kind of intent, like communicative intent.
I feel like that's a good place to stop. Did you have?
Okay.
Yeah, or, I mean, well, obviously.
But yeah, one thing that you need to know is like, yeah, it's extremely good at capturing regularities and systematics, like patterns. So this is why I'm interested in morphology, because morphology is all about patterns in the data.
Can I have a point, please?
Yeah.
Yes, but then we got to hear from Simone, who is
Sure,
graciously silent. Yeah, go on. Yeah.
So the point about mathematics, I think, is an interesting one. So in cognitive science, we have this distinction between system 1 and system 2 thinking, right? Where you so system 1, is all the stuff that you do without having.
Is it in terms of Kahneman? It's fast and slow.
Yeah, same distinction, yeah. And so what we've seen. So what I think of as what the base model doing is more like the system 1 thinking, and then. But on top of that, there has to be the system 2 thinking, right, where you actually implement procedures and do all that kind of stuff. And what we've seen over the last year is a dramatic improvement. So we have these train of thought mechanisms now where it actually implements the system 2 thinking as well, and those tend to do significantly better on math kinds of tasks and so forth. To the point, where it's actually performing in standardized maths tests, it's performing well above, average students. So, I think that's only possible because of the addition of the system 2 part, and that seems to me to be pretty critical, right, to make that distinction.
Sorry, point of clarification, are you saying it is doing the system 2, or are you talking about the adults like Wolfram Alpha doing the system 2?
No, I'm saying it's doing the system 2.
Simone, do you want to?
That's a very good point. I was also going to talk about it for a bit. So just to give you some background, I did my PhD on distribution semantics. That was a while ago, and it was back in the day when Simon was also this latent semantic analysis, and everybody was quite excited about that. So I was curious to see whether we could use this distribution of semantic models to capture something about natural concepts like dogs and cats and chairs and tables and so forth. So, I ventured out quite excited, young PhD student, and found out that performance wasn't actually as great as I hoped. So I started looking for explanations. So what's kind of missing in these models? And I kind of gave up on hoping that we could solve the puzzle by language by itself, right? So, and I've held on to that belief for a very long time. Probably this year is the first year that I noticed that I have to revise my belief and update them, because these large language models do a lot more than I would ever imagined. And I think they even do that in a pure system 1 sense. So it's, from my opinion, it's already a triumph for system 1 thinking. So if we think about the question, so how do large language models compare to humans as cognitive agents? I think this is really a question about, do large language models understand meaning the way that humans do? Do they have concepts the way that humans do? So there's 2 parts to that question. Do they represent them? And do they learn them in the same way, right? So certainly when it comes to representation, if you look at theories about representation, we know that our concepts are grounded in our body. They're grounded in kind of embodied representations. When we think about a concept, it's not only language that lights this up in fMRI studies, but you have all these kind of model-specific regions that contribute to meaning. So that's certainly not alone language. The other thing is, if you look at learning, we learn concepts, complicated concepts like abstract concepts from a very young age, say 10 to 14 months. And a lot of that early concept learning comes from social interaction. So social interactions with our caregivers in particular, like things like gaze following and so forth, are really important. So one of the problems that I have with models as theoretical models of cognition is that they assume the primacy of language. And we have concepts before we have language, and language comes after. So that's a bit of a theoretical limitation, I would say. The other aspect is, of course, language. The goal of language is communication. It's not necessarily, it doesn't serve only representation, right? So there's a bit of a mismatch there. Now, there are really interesting ways in which these models, despite the fact that it's not grounded and it's not embodied, does capture meaning, right? And I think one of the strengths of large language models is that it captures features of how words go occur together, but also these really complicated, higher level, higher order features. And that allows it to do quite impressive things like solving analogies and so forth, right? And so yeah, I was just saying that even though these models don't really capture referential meaning, it captures the relations between symbols, and that also gets a very long way. So altogether, I would say that they provide a very good approximation to this kind of system one, and that system one probably is accounting for 95% of our daily experience. And understanding system one and also the risks of system one, the bias, the stereotypes, goes a long way. So it's implicit, it's fast, it's heuristic, and so forth. But it's really important if you think about the challenges of the day, think about misinformation, think about climate change, for example. The other thing that I want to highlight in this discussion is the problem or the issue of scale, right? So one of the interesting observations of these models is that larger models, scale unlocks new abilities. And as I think this is kind of interesting, but if you go back to for example, the issue of embodiment and grounding. So you see that as these models get bigger, they start to count for, say, visual representations, the representation of the color circle. And actually that information is of course directly accessible to us through the senses, right? But it's never, the amount of information that you need to incorporate is never accessible to an individual. So it might be compensating something. So it might be learning something about the perceptual world that would never be encoded in somebody's language experience over a lifetime. So that's kind of interesting, I would say. So kind of along the same lines, it does this well for certain types of modal information, like the visual system. It doesn't do that quite well for other types of information, like, for example, face. So you don't want LLMs cooking your next dinner. So the second thing is that it's not really clear what it means that this additional scale, the additional corpus, is unlocking new abilities, because the current models, they have a lot of other aspects encoded in it as well. Like attention is an important one. The fact that you have all these different layers that focus on different features of language, right? These are also quite important. But a lot of the older models that didn't have these deep layers, the shallow models that simply predicted words, they were only trained on a fraction of the corpus that the current models are trained on. So it's actually quite possible that a simple model with a huge corpus would also be able to learn this kind of perceptual knowledge from the world, right? And then I think my last point here is the point about agency. So obviously these models don't have goals, and so that's also, it's not really clear what agency in this case means, because these models basically capture all the knowledge that there is on the internet, not of an individual person, not of an individual group of language speakers and so forth. So it's not really clear what the models are. We can pull that information out with the right kind of prompting, but it's not clear what the agent is. And if we compare it with humans, we actively search for information. We just don't let the information come to us because we have preferences and attitudes, and these preferences and attitudes will shape our information landscape. So one of the things that I'm currently interested in is, for example, the differences in the information landscape between men and women, because we know there's a huge difference in terms of the quantity that boys and girls read, and also the quality. So if you believe that large language models are influenced by aspects of the corpus, we should also see differences there. So in terms of agency, one of the major things that I feel that is missing in the current models is that they merely predict the next words, whereas humans have access to other kinds of predictions, and we have other types of objectives. So we probably need multiple objectives. And to give you an example, one of the directions that I think matters is attitudes and preferences again. So these kind of emotional connotations. So we immediately know something to be positive or negative, or aligned with our goals or not. And that information is actually already available before we access the meaning. So the current models don't have that information. And you also see that in certain types of tasks, they have difficulty with this kind of emotional information. So yeah, it needs to capture the good and bad. And I'll probably stop there. And
that sounds good. So Simon, if you want to have a go, and then
Yeah,
I can already see several points of divergence, yeah, yeah.
Is it fine?
Yeah, if you have, yeah.
So I think another crucial point about understanding this large language model is that you need to be careful with the training data. So basically they try to extract as much useful information from your training data as possible. So they might kind of make inference that humans will not ever make in terms of these relations of the words and read what are the spurious correlations you might have in that training data. This is where you get this gender bias, etc. Or for instance, for multiplication was in the paper that I read, like what they learned actually in order to predict this kind of digits of the result, they looked at the correlations of the first digits in numbers, and they found that if you have like both numbers starting with 1, the result will also start with 1. So, so most likely people will not learn such kind of correlations, not really that useful. So the generalizations are qualitatively different. And the other thing is like, for instance, if your data has like bananas and leaves, right? So, and you ask a person like, are bananas similar to leaves? They might say, okay, they're similar because they're both plants. But suppose in your data, you only had like green bananas, green leaves, yellow bananas, yellow leaves. So the model learned that, okay, there's a kind of contextual usage that is similar. It's a color that is makes them similar. Maybe it will know that it's color, hoping that it makes this abstraction. So, but this is something that humans will not ever do. They will not decide that these objects are similar just because they have the same color.
Simon?
So, yeah, so the last couple of points there, well, not the last one, a couple of points. Well, let me go back and say, Simone and I have had many, many conversations about the embodiment issue, and I think that in a sense we've come to the conclusion that it's a kind of half empty, half full kind of problem, right? So my kind of perspective is, geez, it's amazing how much of the perceptual stuff you can get out of language. But acknowledging that you can't get everything. And I think Simone's perspective is more, well, there's all this other stuff that it doesn't get, right? And so in some sense, we're not really disagreeing, right? It's just a matter of where you started.
I agree with that.
You agree with that? Yeah. But the thing about the embodiment that I want to point out, and this was really brought home to me when I was in Ohio, and I had a student that I was on the committee of who was doing her second PhD, and she was blind, right? And so what struck me about that, and in particular, I gave her this exercise where I gave it to the whole class, but I wasn't kind of thinking, and I said, yeah, describe this graph, right? And she just went ahead and did it just fine, right? And had no problems with it. And so, whatever it is that is the embodiment part of what of the story, it's not absolutely crippling to the development of cognition, right? Because if that was the case, then if you're blind, that should be a really serious problem, right? But it's not, right? Because if you're taking out one of the main senses, that ought to be pretty bad, but it's not really.
Can I just comment? So I agree with that, and obviously there's like there have been studies that have systematically looked at that, like how do blind people represent the goal, and indeed they do quite well. But the problem is always the interpretation, right? So there's not a criterion what quite well would be. Like some studies have reported the correlation of 0.20 and said, well, look here, clearly visual information is encoded in language. Others have better results. So there's not a really set criterion to decide what's good enough. I think that's where the cup half full or cup half empty comes from.
Yeah. So, but I guess what I would say, right, is blind people know bananas, right?
Yes.
So there's a lot of really basic stuff that they do. But anyway, as we say, I think we actually kind of really agree, even though we'll probably argue forever. So let me go to where I think the real fundamental problems are, and this really focuses around the amount of input that's required. So the difficulties or the reason that there's like 43 trillion tokens that ChatGPT has to be trained on to do these things are not just kind of subsidiary things that are going to be solved easily because they're fundamental to the nature of the backpropagation algorithm that's used to optimize them. And so, so you can't just scale down the corpus and hope it's going to do well. It simply won't. Right? And what's more, it's built in, right? So if you look at the way the scaling happens, the algorithm is, the fundamental algorithm is what's called a universal approximator. It means it can represent anything, right? That's both an advantage and a disadvantage. So it's an advantage because it means whatever the function is, you can get it. But it's a disadvantage because that means you need all of that additional input. So there are additional inductive biases, structural inductive biases that people have, which underpin the fact that we can learn so much more rapidly. And this is like 5-6 orders of magnitude more rapidly than what the models are learning.
Yeah, this is what I'm very interested in. So I think like cognitive science can also kind of somehow provide some useful information in terms of these inductive biases or any like cognition bias, for instance, so we can incorporate for make this learning process more efficient. And of course, actually not every function can be learned that way, so it should be convex function. And you cannot solve like combinatorial problems by doing the backpropagation. I think
we'll come back to that because I don't think that's quite right. There's certain kind of non-compact functions you can't get, but yeah. So I think that's a really fundamental issue. The other thing where they really do differ is the way that they represent time. So we now have pretty good neural evidence about the structure of the representation of time, and it's fundamentally different from the way that these models are doing it. And so that's another area where I think changes can happen.
Yeah, and one more comment. So they typically also struggle with long contexts. So when you have, for instance, some long narrative, a book, when you read like a human, you have some abstraction, you create this abstraction and you keep it in mind, right? Whereas in these networks, you don't have this kind of ability to accumulate these extra contextuals, like contextual activity.
So we're timing wise so that we could change tack a bit and talk about what this means for cognitive science. But I think that would mean you're both very rushed and there's no time for questions. So instead, I might just continue to just like push a little on this topic and you can bring in the points for cognitive scientists because they're coming out naturally anyways. But I wanted to sort of to drive that along. One of the things I'm seeing here is dancing around different kinds of meaning of the word meaning. So there's sort of what is the representation in the head, and then there's like what Kat was saying was like, do they know? Like, which is kind of almost a meta meaning. And I wonder if you have thoughts about either what, different senses of meaning, the extent to which the LLMs have them, and also what that means for us as cognitive scientists, or how that maps onto how we understand humans in the world. Anyone can say that.
Okay. So I think meaning, consciousness, a bunch of these things are really tough to get your head around. So I do actually like the Turing test. I know a lot of people don't like it, but I like it because in my opinion, it's very hard to say because so the answer is yes and no, right? So people talk about to what extent are they building a world model in their representational architecture. And so there's a recent paper about a network that was designed to learn Othello. And if you look at the hidden unit representations, you can see the board, you can see its ability, its sense of where the possible moves are and all of that kind of stuff. So it really looks like it has built an internal representation of the world, which is Othello. But my suspicion is that it's not as complete across the spectrum. But my suspicion is that people are not as complete across the spectrum as what we think they are either. So I think there's lots of gaps in the kind of systematicity of the way that people understand the world that never get probed and therefore are not highlighted. So, but I think it's a research program to answer the question.
I agree with you. I think indeed the models probably have some kind of world model, but to construct that world model, they do need a bit of agency. So there's no incentive, there's no agency there. The other thing is, of course, they might have meaning, but it might be meaning in AI sense. It doesn't necessarily compare to human meaning. So I don't know if we can just talk about meaning in general, or meaning similar to the way that humans have meaning. That kind of goes back to the primacy of language argument. That's a reasonable assumption.
Can I just say about the primacy of language? So one thing to note about these models is that they're sequence models, right? They're not, there's nothing about them that forces them to be language models. And so the only thing that at the moment that makes them language models is the fact that they're only trained on language. But you know, it's conceivable that if we had the capacity to actually you know, record other senses the same way that we can get language tokens, that we could, you know, make them much more comprehensive.
So yeah, and I'm also really looking forward to multimodal models, and I think they will address a lot of the shortcomings. But at the moment, the problem is that because these large language models, they are so predictive that we start assuming, we're starting to retrofit our theories to the model, right? So we say, okay, they predict all kinds of behavior, so it must be language that's driving that. So, and that's a bit of a problem. I'll hold that thought there, but so one of the directions forward, I think, is to start this kind of coming up with a better resource to train these models. Like, okay, what would be the appropriate corpus, for example, right? Should it be trillions of words? Probably something more in the order of 100 million of words. So I guess one of the exciting directions here is things like the baby large language
There's a
models
challenge baby LM.
Yeah, and that's just
to replicate the process of language acquisition in kids.
Yeah.
So they created the speech corpus for kids, and the challenge is to replicate the stages.
So do you think that's possible though? Because like what some of you have said, and my understanding is the fundamental, a fundamental thing that's different is that they don't have the inductive biases we have, right? We can learn so much from so little because and so how does that, do you think that will work?
Yeah, I think it will work if we incorporate some inductive biases. So it will allow them to learn more efficiently at least. So you don't need to have this billions of tokens to train on. And
I also think, so the baby LM corpus was just released, I think, last month. It contains kind of data that you would get up to 13 years old. But again, the problem is that it's just a corpus, so it doesn't distinguish between the input of an individual child, right? And if you look at language acquisition, there's a huge amount of variation in how children acquire language, both in terms of the quality and the quantity. So if you look at it from like, okay, what can large language models offer according to science? I think that's a limitation. We have to kind of look at individual models, right? So what would be the individual input somebody gets, and try to kind of take that into account. So that's kind of where I see things going forward.
Yeah, and I think it's not only the individual corpus, but it's the fact that the language is learned interactively. And so you know, not a, you know, parents are modifying the nature of the input that they're giving based on what the child is saying, you know, where that particular child's gaps are and so forth. So you literally have to, you know, raise the LLM within.
Yeah, I think it would be great to incorporate some kind of instrument to create hypotheses. So because children, they are modeling words, right? And those are not modeling the word. They're not coming up with the hypothesis as humans would come up. So they would provide a hypothesis about the word, and then you check it on the data.
Yeah. So I'm not sure about that. So I would like to make a clean distinction between structural inductive biases and content inductive biases. So when I say a structural inductive bias, I mean a way that you might change the architecture of the language that would change its the rate at which it's able to generalize, as opposed to building in specific content inductive biases, like, you know, here's a set of concepts that already exist a priori, and it's a matter of selection from those concepts, as opposed to actually accounting for the development of the representation of those concepts in the first instance. And that's where I feel some of our models of particularly word learning, are really not sufficiently comprehensive, because they don't actually address the question of where the concepts come from in the first instance.
So I'm gonna stop here because we've got 10 minutes. I want to take some questions from the audience. If you don't have questions, I have plenty, and I know there's a bunch in the chat, right? Are there?
No questions, Shane.
No questions. Okay, so if you are online and have a question, just put it in chat. Simon Cropper is monitoring it, but also we can start with one from here, and yeah. So yeah, Jen.
I really can't remember the name off the top of my head because it was quite a while ago now. But there was some talk a while ago of like smaller parameter models that could be trained off large models that could perform like pretty well compared to equivalently sized models trained straight off a corpus. And I don't know how that factors into like some of the thoughts you've been having, like, because considering the fact that humans are sort of trained by other humans rather than just by like passive, yeah.
It's kind of distillation learning when you just have sort of like an expert model and the student model, and student model is much smaller size, and you kind of compressing the knowledge from this larger model and making it more kind of efficiently represented. And there is also an interesting debate in this particular area in terms of predicting the reading time, like behavioral characteristics from humans. And there's a bunch of work that claim that the smaller models are better than the larger ones of this one.
Can I just ask just a point of clarification? So there's two different kinds of ways I can interpret what you're saying. So there's a whole line of work where you kind of use output from the larger models to train the smaller models, and that and in all of these kind of reasoning tasks, more of the system 2 kinds of tasks, that seems to be better. There's another way in what you're saying could be interpreted too, though, and that's that you're doing fine tuning. So so there's a way where you can have the big model, and then you can, alongside it, you have another model, and you train it on a small corpus, and the two models are actually used kind of together, and and you just change the small model, you don't change the big model, and that allows you to fine tune to specific contexts more rapidly. So which of those were you thinking?
I think I was thinking about the first one.
The first one.
Yeah, and I think they also use that as a way to cheaply train models, right? Because not everybody has the capacity to train GPT-4. It takes $100 million to do so,
Yeah.
right? But I think this is interesting from a cognitive perspective, because obviously the representations in ChatGPT are immensely complex. Nobody really understands. So there's always going to be the need, and this is something that we are very skilled in extracting representations from a black box. So you can imagine that for our kind of theories, it can be useful to kind of come up with a low-dimensional extraction or distillate from that model and use that to test our theories on, because that will allow us to kind of make it computational attractive, but also eventually gives transparency in it.
Thank you.
Sorry, can I just follow up on that? So this I think is important in terms of understanding, is cognitive science dead, right? Because so one of the challenges, right, is we have these models that actually do a whole bunch of stuff that we have never been able to do before, and do it extremely well, and yet we still don't actually understand how they're doing it. And so my feeling is what's going to end up happening is that we're going to have this change, or a split in levels of analysis. So we'll have one level of analysis, which is the kind of neural level, and then we'll have another level of analysis, which is more in the same space as what a lot of the cognitive models currently exist. And that's going to be, they're both caused, so I'm not talking Mars levels here, I'm talking about two fully causal levels. And I think that's going to be necessary because a lot of the phenomena we're only going to be able to understand with theories at the higher level.
Yeah, I think this point is very important in terms of also interpretability, because the model might arrive to the correct prediction, but in a completely different way than humans. And there is a bunch of work existing in NLP that also tries to estimate the computational graph that the model uses to arrive, for instance, to solve this arithmetic problem. So, and when you extract, you will see that it actually uses completely different facets. It still arrives to the correct answer.
Any other questions? Simon, any?
Not in the chat.
Well, I have one. Oh, no, yeah.
Right to the beginning with you, Simon, with the idea of attention onto particular words and to various degrees, and the concept of meaning and what it means by meaning, and to what degree does that relate to consciousness? I mean, I'm throwing out a bit of a wild question here, but is part of the concept of consciousness in order to fine-tune the attentional mechanism? And if so, does GPT-5, I'm going to be really provocative, need to be conscious to make the next step?
So I have something to say on this, but
Okay, so the next one's touch that.
So I've been a real consciousness skeptic. So I didn't really believe in consciousness up until probably last year. And
With humans?
with humans, yeah. And but let me separate out different pieces, right? So there's consciousness, which is about the voice in the head, right? Which is the do I actually rehearse what I'm going to say before I say it and so forth. So I think that kind of thing happens. The whole qualia stuff, I have no intuition about that. When people say that, it just it doesn't register with me at all. But the voice in the head does. And one of the things that really struck me, but I've always kind of wondered, well, why? Why is that thing there? And there was this paper earlier in the year which talked about reflection. And so this is reflection with an X. And so it's what it does is it's a specific model, and it basically just tells the model to think before it actually produces a response. And so there's a whole bunch of, so it's doing prediction still, but all of those tokens go into the context, but they're never output to the outside world, right? So it's as if it's kind of going through its own internal mental operations. And what struck me about that is that there are cases there where you have exactly the same model and you ask it, just give me the answer. And it was on some tasks it was getting like 10% right, and then you just got it to do this reflection thing, and then it went up to like 90% correct, right? And so again, this harks back to the system 1, system 2 stuff, right? And so that kind of what was finally convinced me that there's actually a reason that there would be that voice in the head, right? That it's really implementing the same thing that this reflection is doing. And so that's now my kind of working model for consciousness is.
You think it does some reasoning?
Yeah, and it's doing reasoning that is not presented to the outside world, but it has to be trained to do the reasoning. But you can see, because in the model you can actually look at what it's doing when it wasn't responding, right? And it's definitely going through a chain of reasoning.
So that will be needed for GPT-5.
Well, it already exists. You can do it with GPT-4.
Oh.
Okay, one more question and then we'll go. Go ahead.
Do you think that with a large enough box of information that's able to actually process, would be able to compensate for all these things that you say that it can't do currently? So if you just have, just all of the information available on the internet, I'm talking everything, does that mean that it would be able to compensate for the fact that it isn't able to reason, or that it isn't able to solve complicated math questions that haven't been done previously? Like, is that possible?
Can you learn multiplication of 3-digit numbers by just looking at millions of examples? So this is the question. So basically, when you have this math problem, right? So basically, if they try to fine-tune this model, so millions of such examples, and it didn't learn this still. So you need to know this algorithm, that you need to start with the last digit multiplication, then you have some remaining part, you move it to the next register, etc. So the only thing that it can do is just to find some useful correlations between the digits and memorize whatever it saw.
So I'm going to
That's my point.
Yeah. So I think so when you do give it the ability to actually do the thought in between, and you give it the training set which goes through the procedure, right, as kids would have, then it does significantly better. And as I said before, it is performing very well on these math tests. You're better than most people. So I don't think that's a fundamental problem. I think it's difficult to say, whenever you start to want to make a claim about there will be no things that it can't do, that's a very difficult claim to try to support, right?
Okay, so we're about over, so I'm just gonna sort of haphazardly summarize. It looks like everyone's in agreement. They're really good. There's some things that are different. We're not sure what they are. Sorry, this is just the most vaguest summary ever. I think, but embodiment, the nature of meaning, the fact that humans are agents and we learn off of very little, those seem to be the key differences of both interest and points of sort of possibly, really interesting for our science. I don't even know why I'm trying to summarize it. You guys were all here. Anyways, thank you for coming. Thank you especially both Simons and Kat. It was a great, really very interesting discussion. So,